So our plan is that we will have a test tomorrow, and on the test, to help you out, is going to be probably this whole section. Okay, so I may like not list the variables, but the variables are just the things that are represented by the letters in the equations, right? So you guys can definitely expect to have those 4 equations on your test tomorrow. So you don't have to have them memorized. You can look at the front of the test and they'll be there for you. Because what I want to know is, can you apply those, not can you memorize them? It's not actually an objective of physics class to memorize equations. It is an objective to be able to use them. So we will use them for our test and not have to memorize them. You can if you want to, but you don't have to. Okay. So we had 6 problems, I think, to do, starting with our water skier friend here. Water skier should be blue. All right, so on our review sheet, problem number 1, an 80-kilogram water skier is being pulled by a boat with a force of 220 newtons, causing the skier to accelerate at 1.5 meters per second squared. Find the drag force on the skier. So the first thing that we should do with problems that involve forces is draw a force diagram so that we understand what the forces are and which ones are relevant. So there's a dot that represents my skier. I know that he's going to be experiencing some kind of gravity, and he's going to be experiencing an upward force that you could call normal force, I suppose, because it's just a name, right? In water, sometimes we like to call it buoyant force, so that he's floating. It could also be buoyant or normal, or it could be lift, right? Is when you're moving through a fluid, and you have some velocity, then you end up with lift. You can call it any of those things. It doesn't make a difference to me as long as you recognize that there's some upward force. If our skier is not accelerating up and down, then we would also anticipate that those forces are balanced, so they have the same magnitude as each other. We're told that he's being pulled forward with a force of 220 newtons. So whatever that pull is, it's equal to 220 newtons. And we're being asked to find the drag force. So that's going to be the force backwards. And we don't know what that is. We're going to try to find it. The other pieces of information that we have are the mass of the skier, which is 80 kilograms, and we're being told his acceleration. Okay. So we know that if we want to figure out a force on something, that we can use a net force equation to do that. So if we know either the difference or we know both the mass and acceleration, we can figure that out. So here's our net force equation. It's going to be equal to mass times the acceleration. We know both of those pieces of information. That's going to be equal to our drag force plus our pull. So if what we're trying to solve here is drag, I'm going to isolate that. So I'm going to focus just on the last 2 parts of this, so that I've got drag is equal to my mass times acceleration. Wait, not divided by. I knew it as I was doing it that it was wrong. It's going to be mass times acceleration, and then minus my pull. All right, so my mass here is 80 kilograms. My acceleration is 1.8 meters per second squared, and our pull is 220 newtons. So when I solve this, 80 times 1.8, this would be 144 newtons, because kilograms times meters divided by second squared is newtons, minus 220 newtons. It's going to give me minus 76 newtons of drag. So that's what this has to be. Does that make sense to us? I think so, because if we have our we expect that the magnitude of our pull is greater than our magnitude of our drag because we know that he's accelerating forward. The difference between those two magnitudes, if I do 220 minus 76, so I just added them together, I got 144, which is that number, right, which we expected. And if I divide that by my mass, which is 80, then I get 1.8 meters per second squared. So I can solve it backwards and get the right values out of it. So our answer for that one should be minus 76 newtons. How'd you guys do on that one? Good? Okay. Number 2, a 2,000 kilogram car is slowed down uniformly. This is telling us a negative acceleration from 20 meters per second to 5 meters per second in 4 seconds. Determine the average net force on the car during this time and how far the car traveled. So we need to solve for our net force. It's one thing we need to know. We also want to know our distance it's traveled while slowing down. All right, what are the things that we know? The force things that we know are 200 kilograms for our mass. Do we know our acceleration? Nope. And we don't know our net force, but that's one of the things that we need to solve for. So if we're trying to find net force, we're probably going to need our acceleration. For motion variables, things that we know are our initial velocity is 20 meters per second. Our final velocity is 5 meters per second. The change in time that takes place is 4 seconds. And we're being asked to find our change in position. So it looks like what we're going to need to do first is take these 3 things and solve for a fourth, solve for acceleration, and then use acceleration to solve for net force here, and also solve for displacement. So if we take a look at our equations, we know that we're going to need to use force equals mass times acceleration up there. And over for our motion stuff, let's see, we've got a final velocity. We could just use final velocity is equal to acceleration times time plus initial velocity to solve for our acceleration. And once we have acceleration, we can do our change of position equals 1/2 times acceleration times time squared plus initial velocity times change in time. All right. I'm going to rearrange some things with this one first. So to isolate the acceleration, I'm going to subtract my initial velocity from both sides and then divide by the change in time. So acceleration is final velocity minus initial velocity divided by change in time. So we're going to have 5 meters per second minus 20 meters per second divided by 4 seconds. 5 minus 20 divided by 4 gives me minus 3.75 meters per second squared. So that's my acceleration. We expected it to be negative, right? Because it was slowing down uniformly. And then to find our distance, our displacement is equal to 1/2 times minus 3.75 meters per second squared times 4 seconds, and that value is going to need to be squared, so it's going to need to be divided by or multiplied by 16. Plus our initial velocity, which was 20 meters per second, times 4 seconds. Okay. So I've still got my minus 3.75 in my calculator. I'm going to multiply that times 0.5, and I'm going to multiply that times 4 squared. So the first term here is going to be minus 30 meters. We're not expecting to be going backwards, are we? And then 20 times 4 is going to give us 80. Positive 80 minus 30 is going to give us a displacement of 50 meters. Lastly, to solve for our force, so we did this one first, This one second. This one third. Our force is going to be equal to our mass, which for our car was 2,000 kilograms, times our acceleration of minus 3.75 meters per second squared. So 2,000 times minus 3.75 gives us minus 7,500. The units should be newtons. This seems reasonable because if we are slowing down uniformly, we're going to expect our force to be opposite the direction of motion, right? So the negative sign is telling us it's going backwards against its motion. Do you guys have any questions about number 2? No questions? All right, so we solved for our 3 things. Next, baseball. It's baseball season now, right? I feel like when I was in high school, it rained all the time in the spring. Like half of our games would get canceled because of mud. Sometimes we would play in the mud. That was kind of not as much fun. Do you play softball, Garrison? No. Okay, so some baseball pitchers are capable of throwing a fastball at 100 miles an hour. The pitcher achieves the speed by moving his arm through a distance of 1.5 meters. Determine the average net force that must be exerted on the 0.15 kilogram ball during the pitch. All right, so what do we know? We know that our force things here are, we know our mass is 0.15 kilograms. It's pretty light. It's not a shot put, right? Do we know our acceleration? No. Do we know the distance that's traveled? We do know the distance, but we don't know force. So motion stuff is going to be, when a pitcher throws a fastball, what's the initial velocity? That's going to be 0 meters per second, right? It's not moving before you throw it. We know that the final velocity here that we're given is 100 miles per hour, but that's in the completely wrong units. We're going to have to fix that. We're told that the distance that is traveled during the acceleration of the ball by the pitcher is 1.5 meters. All right. So if we need to figure the net force, the first thing we're going to need to do is figure out the acceleration. And so luckily we know 3 things about the motion, so we're going to be able to do that. First, though, I'm going to convert my final velocity here into meters per second. So if I've got 100 miles per hour, I need to convert miles to meters and hours to seconds. And to do that, I'm going to use dimensional analysis. We're actually given that 1 mile is 1,600 meters. And so I want to get rid of miles. So I'm going to put that in the denominator so that they cancel. And then 1,600 meters in the numerator. So now I have meters per hour. To convert hours to seconds, I'm going to say that for every hour, I have 60 minutes. And in every minute, I have 60 seconds. And then my time units cancel. Hours cancel and minutes cancel. So that I'm left with meters per second. And then calculating that out, oh, I think it's 44, but I'm just going to double check. And divided by 60, divided by 60. Yeah. So I got 44.4 meters per second for my final velocity. Seems pretty quick. Next thing to do is figure out what my acceleration is using my initial velocity, final velocity, and distance. So I think that the one to use is going to be my last equation on our equations list. So my final velocity squared is equal to initial velocity squared plus 2 times acceleration times the displacement. So I'm going to solve for acceleration. I'm going to rearrange this. Acceleration equals, and the first thing I'm going to do is subtract my initial velocity squared from both sides. So my final velocity squared minus initial velocity squared, and then divide that by 2 times the displacement. So my final velocity is 44.4 meters per second squared minus my initial velocity, which is 0 squared. So that makes life easier. And then 2 times my 1.5 meters. So it's divided by 3, basically. So I need to know 44.4, and I still have that in my calculator. I'm going to square that. Answer times answer. That seems very large. Yeah, that's better. Oh, I know. I hit the caret, didn't I? I did 44 raised to the 44. That's what happened. Okay, so I've got 1975, and I'm going to divide that by 3. So what I get for my acceleration here is 658 meters per second squared. Does that sound right to you guys? Yeah? Cool. Pitching is hard. I'm always impressed by pitchers. All right, so 658 meters per second squared. When I know that information, now I can calculate my force. And what I'm going to do is take that acceleration and multiply it times the mass. Like I'm out of space here on my paper. So my net force is equal to 0.15 kilograms times 650. Sorry that that's messed up like that and down there, guys. When I multiply those two things together, what I get is 98.8 newtons. I think that seems reasonable. I always try to compare these to like how much, if I can imagine how much force that is, that would be as much force as it takes to hold up something that weighs about 10 kilograms. Right? That's doable. We can do that. Yeah. It's just when you have a tiny baseball, you're going to get to throw much harder. Okay. Anybody have any questions about number 3? Cool. All right. So number 4. After falling from rest, so that it's from rest tells us something about the initial velocity, at a height of 30 meters, a 0.5 kilogram ball bounces upward, reaching a height of 2 meters. The contact between the ball and the ground lasted 20 milliseconds. Find the average force exerted on the ball by the ground. Break the problem into pieces, do a bunch of kinematics, and then apply Newton's second law. Okay, this one's a little bit tricky. So we'll see how you guys did. The idea here is that you have a ball that's going to fall down. Right, so it starts up here, falls down, hits the ground, right, and is going downwards, and then squishes and then bounces back upwards to a new height. I'm going to try to use different colors here and keep this a little bit straight. So if it falls from a height of 30 meters, which is pretty high, right, it's going to fall from 30 meters, hit the ground, hits the ground, and then bounces back up to a 20-meter height. So where would 20 meters be? Something like this. 20 meters. Now, what to keep in mind here is that up at the top here, our velocity is 0 meters per second. Oh, velocity is 0 meters per second up at the top, right? Because when the ball reaches the top of an arc, its velocity is 0. I'm trying to color code it. That's why I want to change this. Over here, our velocity is 0 meters per second. And what we're interested in is the force exerted on the ball by the ground. This is the final thing that we're trying to figure out. So in order to do that, what we have to do is figure out what is the acceleration here. What is the acceleration when it changes direction and speed at the bottom? In order to do that, what we're going to need to know is what is our velocity here and what is our velocity going upward. So here's the way that I like to set this up, because there's kind of 2 parts. I know we're used to thinking about things as initial velocity and final velocity, but it's a little bit easier if you think about it in terms of Here's velocity 1. This one's velocity 2. Then the upward velocity when it bounces back up is velocity 3, and then velocity 4. Does that make sense? Because otherwise what we're doing is looking at the blue part first and saying initial velocity and final velocity. And then over here, initial velocity and final velocity. But we're going to ultimately end up with this is the initial velocity and this is the final velocity. So everything just gets flipped around a bunch. But if we think about it in terms of 1, 2, 3, and 4, we can kind of keep things a little bit more organized. So that's one trick that I do when something has 2 steps, is just I start numbering things and instead of saying initial and final, and then applying the equations as we need to. Okay, so the first thing that we have to figure out is what's this velocity when the ball hits the ground? Well, there's another piece of information that we know is that when the ball is either in this blue section or in the pink section, we call them the blue and the pink section. Here's blue. Here's pink. We know what the acceleration ought to be there because in both cases, what applies is acceleration due to gravity. That's not what applies when it bounces. But if that is what applies while it's falling. So we've got 10 meters per second squared for both of those. And that's important because it's kind of like the unseen piece of information that we need to know. We know that the displacement in the first part is 30 meters, and the displacement in the second part is 20 meters. We know that our initial velocity in the blue part, sorry, I'll just make it velocity 1, is 0 meters per second. And we know that our final velocity in the pink part, velocity 4 is 0 meters per second. So since we know 3 pieces of information for both of those, we can figure out the other stuff. So for the first one in blue, what we have to solve for is velocity 2, which is going to be treated like final velocity for that section. And if we look at our chart here, if we have initial velocity, final velocity, position, and acceleration, we ought to be using our third equation here. So that's what I'm going to use to figure out our velocity 2. So the equation says final velocity equals final velocity squared equals initial velocity squared plus 2 times acceleration times the change in position. So if that's the case, what we're going to do is change our final velocity squared to velocity 2 because that's the final velocity for that part of the motion. So I'm going to make this velocity 2 squared, and I'm going to make this guy velocity 1 squared plus 2a delta x. What we need to find is that final velocity, so that velocity 2. The initial velocity was 0, so yay, that makes life easy. Plus 2 times our minus 10 meters per second squared times the distance traveled, which was 30 meters. So that's going to be equal to 2 times minus 10 times 30. Gives us minus 600. What do we think of that? Oh, we missed a sign. We needed a negative sign here for our 30. The problem is if we get an answer like minus 600, it's not going to work because since this is squared, we're going to have to do the square root of it. That leads us to an imaginary number. So this needs to be negative. So that's going to be positive 600 meters squared per second squared. So velocity 2 is going to be the square root of that value. So square root of 600 is going to give us 24.5 meters per second squared. Oh, meters per second. Sorry. So over here, 24.5 meters per second. And that's downward, right? So what makes sense for that is that if our result is the square root of something is going to be plus or minus. So this value needs to be minus 24.5 meters per second squared. To figure out velocity 3, what we're going to be doing is looking for the initial velocity for the stuff that's happening in this pink part of our motion. And so we can use the same equation, except we're going to be solving for initial velocity. So this time we're going to have I'm just going to rewrite my equation. I'm going to say that this is going to be velocity 4 squared. It's equal to velocity 3 squared plus 2a delta x. Velocity 4 squared is 0 meters per second. That's going to be equal to velocity 3 squared plus 2 times minus 10 meters per second squared. Here our displacement is upward, so that's going to be plus 20 meters. We don't need to make that negative this time. So we have 0 equals velocity 3 squared plus 2 times minus 10 times 20. So this is going to be plus minus 400 meters squared second squared. So I need to add 400 to both sides. So my velocity 3 squared is going to equal 400 meters squared per second squared. And velocity 3 is going to be the square root of 400 meters squared divided by second squared. So the answer for that part is going to be plus or minus the square root of 400. So plus or minus 20 meters per second. What do you guys think? Should be positive or negative? It's going upward, right? So it needs to be positive. All right, kind of running out of space here a little bit. But so what we need to do to figure out this acceleration here in the middle is we need to look at that acceleration is the change in velocity divided by the change in time. And that's just from this first equation. So even if you get stuck on that part, you can come back to this equation, use it, because we have initial velocity and a final velocity and change in time. So to figure that out, our down here in this interaction with the ground, the final velocity is going to be the upward velocity from the pink part, which is our 20 meters per second. So we're going to have 20 meters per second minus, because we're looking for a difference, our negative 24.5 meters per second. And then all divided by our 20 milliseconds. So if we want to know how many seconds is in 20 milliseconds, so 20 milliseconds times, for every 1 second, we have 1,000 milliseconds. Divided by 1,000, it's going to be 0.02 seconds. All right, so if we do 20 minus 24.5, we're going to end up with 44.5 meters per second divided by 0.02 seconds. So our acceleration is going to be, I have 2,200 meters per second squared, which is a lot. And then to figure out what the average force is, our net force is going to be equal to our mass times our acceleration. The mass of the ball is half of a kilogram. So if we do our 2,200 meters per second squared by half, we're going to end up with 1,100 newtons. So that's our final answer. That's a lot of force, right? That's a lot more force than our person throwing the baseball over here. It's 10 times as much force to make something bounce. That's pretty cool. All right, what questions do you guys have about that one? I know that's a little bit tricky because it really feels like it's like 3 problems instead of 1 problem, right? You guys have any questions about it? No questions? Okay. Just make sure we get through all these and don't run out of time. All right, in the diagram below, where we have our 2 kids on a sled and someone's pulling them, the cord makes a 25-degree angle with the horizontal. The mass of the sled and occupants is 100 kilograms. So here's my angle. The tension in the cord is 120 newtons, and the friction force is 15. Find the acceleration of the sled. So what we're going to need to do to solve for this is we're going to need to make a force diagram and then a net force equation for Newton's second law. All right, so force diagram. We've got gravity downward and normal force upward. Since we're on a horizontal surface, it makes sense that we make our axes straight up and down and don't tilt them, right? We're going to have a forward pull coming from that rope. It's going to be a component of that. We're also going to have a force backwards. We know the friction force is 15 newtons. Gravity for our sled, since they weigh 100 kilograms, this is going to be 1,000 newtons downward. We don't know what normal force will be because it will depend on that tension in the cord. So if I'm looking at my tension this way, we're going to have tension. Let's see, that's 1,000. I'm just going to make this kind of short. So here's our pull. We know that at this angle, it's 120 newtons. We know that this angle is 25. And we're going to have some components here. We're going to have one component that's horizontal and one component that's vertical. And these 2 verticals together are going to add up to oppose gravity, but it's not actually asking us to do anything with the vertical, so I'm just going to not worry about it. I'm going to focus instead on this this component of the pull that's in the horizontal direction. So I called that FPX. All right, so if I want to figure out what FPX is, because where we're headed is we're going to need to set up an equation where our net force is equal to the mass of the sled times acceleration, and that's equal to the pull in the horizontal direction plus friction backwards. We're asked to find the acceleration, which is going to be this guy. We know mass, we know friction. We need to solve FPX. So in order to do that, I'm going to take our triangle, 120 newtons are 25 degrees, and we're going to solve for that side. That's a right angle. So this is an adjacent angle, or an adjacent side to the 25-degree angle. So when we solve this, we're going to use cosine. So cosine of 25 degrees is equal to our component of that pull force divided by the total pull force, 120. So our FPX is going to be equal to 120 newtons times the cosine of 25 degrees. Handy calculator, 120 times cosine 25. Gives me 108.8 newtons of force. So now that I know that, I can put it in my equation. I've got 100 kilograms for my sled and my riders times acceleration, the thing I'm trying to solve for, is equal to positive 108.8 newtons plus my minus 15 newtons in the opposite direction. So my acceleration will be equal to my 108 minus 15, which is going to give me 93.76 newtons divided by 100 kilograms. So I've got 0.94 meters per second squared. So every second, he's going a meter per second faster, approximately. What questions do you guys have about number 5? That one was a lot easier than number 4 was. Lots faster. Okay. Last one, number 6. A skier going down the hill, and we have to figure out his acceleration. So someday when we have the Olympics again, you guys can use their data to solve for it. No? Maybe. Think about it. Or at least sit there and think to yourself, I could calculate that, and then just enjoy the skiing. Okay, so we've got a 60 kilogram skier going down a 35-degree incline with the coefficient of friction. So when I see coefficient of friction, that tells me, okay, I'm going to need to know normal force. And I'm going to need to use that to solve for friction. We need to determine the acceleration. So where we're headed with this guy, we're probably looking at net force equation problem. Our mass times acceleration equals the forward component of gravity pulling him downward, which is going to be horizontal or parallel to the surface. So FGX plus friction backward. We need to solve for this stuff. In order to get friction, we're going to need to know what our normal force is as well. So here's our force diagram. We've got gravity downward. He's on an incline, so what's going to end up making sense is that we draw our force diagram also with an incline in mind. So here we go. We've got a tilted axis. Our gravity is going to be broken up into two components. We're going to have a downward component, FGY, that goes into the hill, and FGX that's pulling him down the hill. We predicted that already. Normal force is going to be opposite FGY. As long as he's not going into the hill or accelerating upward, we would expect that those would be equal. And then we're going to have to find friction backwards, which we can do after we figure out normal force. So the next thing to do is figure out where our angles go. In order to do that, I just like to extend this out a little bit and imagine that this is a 90-degree angle. And so if that's the case, and I've got a 35 down here, I'm going to have a 55-degree angle up here. And if I wanted to solve for this angle that's opposite, this should be the same magnitude. That side of the triangle should be the same magnitude as this triangle over here. If you did it a different way, it's very likely you got the right answer and you just did it a different way. So here to solve for, sorry, that's not friction, that's FGY. So if I want to solve for FGY so that I can get at normal force, that's going to be the opposite side from 55. So if I use the sine of 55 degrees, that's going to be my FGY divided by FG. To solve for FGY, we do FG times the sine of 55 degrees. For a 60 kilogram skier, I'm looking at 600 newtons for FG times the sine of 55 degrees. So I got 491 newtons for that. Minus 491 there, which means normal force is going to be positive 491 newtons. If I want to solve for friction then, so friction is going to be equal to the coefficient of friction times normal force. We're given a coefficient of friction of 0.08. We multiply that times our 491 newtons, get 39.3 newtons. That's going to need to be negative because of the way we've drawn our force diagram. But now, let's see, I still need FGX. So to solve for FGX, I'm going to look at this triangle again, only now I'm going to use the cosine of 55 degrees because it's the adjacent leg. So cosine of 55 degrees equal to my FGX divided by FG, which we already said was 600. So FGX is going to be 600 newtons times the cosine of 55 degrees. I got 344 newtons. So now that I've got both of those values, I have both FGX and friction. I can go back to my net force equation to solve for the acceleration. So we've done before, acceleration is going to be the sum of our forces divided by the mass. So here FGX is 344 plus our negative 39.3 divided by the mass of our skier, which was 60 kilograms. So I got 5.08 meters per second squared. How'd you guys do? Cool. All right. So we're gonna have our end of the unit quiz tomorrow.